So friends, we are into the third lecture of the 7th week, and we'll continue discussing the fault diagnostic techniques. So it is a fault diagnostics part B, and in the next lecture, that is fourth lecture, we'll discuss root cause analysis, which is very useful technique when we have a system which is very complicated, sorry, not complicated, complex systems, and they have a high stake in terms of their continuous operation, and they have very high stakes that they should operate very safely. So let us discuss some more techniques of fault diagnosis, because eventually what is our objective? These techniques should be operating as a procedure in a machine learning algorithm. That means online data, and then it will tell you that component, if component fails, that is something like operator advisory system. How you can correct it, how we can avoid the failure, or what action to be needed, and what you should check to perform a correct diagnostics and draw the inference, of course. So the scope of this lecture remains into real-time surveillance and monitoring. I have first-hand experience of real-time surveillance and monitoring, though it may be having some limitation, because these are the techniques they have born with the advanced systems like process system, and then chemical systems, nuclear systems, and then transport systems. And I think the society got benefited through real-time surveillance and monitoring, because they enable very high coverage. In a train, you will find an operator cabin where he keeps monitoring the system, operating parameter and safety parameter. Similarly, in a plant control room of a process or chemical or nuclear industry, a person monitors the process parameters and some of the direct equipment parameters, their health and all. So, but then there is always to go or learn and improve the system. So we have this fault tree, event tree technique that we have, and then in fault tree event trees, from a huge document, these inferences are drawn and they are converted into the rules. And suppose this could be quantified, qualitative both. And then fishbone diagram, and we have been seeing in our reliability or management literature, these are the diagnostic tools. They are also called cause and effect tools. Precursor analysis, it has got its origin somewhere in the probabilistic risk assessment. That means whatever event has happened, we should be able to map it on a PRA model of the plant, and we should see whether it is having any trace of contribution to the plant unsafe states, and that will tell us which category of diagnostics or prognostics should be performed for this. If it has serious consequences, then we have to have a serious consequence, and I'll show you what are the level of detail that need to be investigated. Pareto analysis is there. In one word, if somebody has to define, it is a 80-20 rule which is implemented for cause and effect type of subjects. So real-time surveillance. Let me spend some time on this slide. What I am trying to put it, because in literature you won't find this in a formal way being talked about or be delivered as a lecture actually. So we can say the present mode of monitorings, they are either from control room of the plant or in the local area, because the equipments are not located in the control room, they are located in some areas where quite possibly a dedicated staff has been put to monitor them. So, in a control room, it is surveillance. That means all the information is coming, and the various trips and parameters, they are brought to the control room, and continuous monitoring is going on. Now, what to do for continuous monitoring? If any parameter is changing its state from safe state to or alarm state, there is a audio visual signal will be there, and it will draw attention of the operator what has got deviated. 90% of the time, it is some minor corrective action that is required to start something, stop something, close a valve, open a valve. If it is electronics, something is there, then repair the card, replace the card is the easiest thing which can happen. If it is an electrical system, then some alarm is there, then you see why the alarm has come. It is some under voltage relay has failed, or some problem is there, because the actual power supply has failed, and now our plant dedicated power supply system, captive power, diesel generator and all, they are starting. So, it is a situation of transient. So, this is called a surveillance, and for every case the objective is same: bring the plant to normal operating state or normal shutdown state. So, this is how input for surveillance. And then as we are telling, test and surveillance. Test and surveillance means some systems, they are remaining passive mode. So, unless until there is some situation or activation, then only they will come to. So, there the periodic testing. So, surveillance and test in the control room, these are the followed. Now, timely detection and assessment of any deviation. So, this is the objective function of surveillance and test and surveillance and monitoring. Monitoring is simply keeping a watch on the parameter and steady state readings that we are seeing, and we have a mental model what should be the reading on instrument when the plant is operating, when plant is shut down or plant is in any other state. So, those templates should be matching with our mental mapping, So, this is a time tested plant surveillance. If we say that in today's world, my plants have operated safely, the credit goes to the real time surveillance and monitoring actually. It has got some limitation also, but that's how the new techniques are coming, but it has done well actually. If we say that this industry has done well, that means this kind of monitoring, real time surveillance monitoring should get the due credit to this, and credit should be given to the designer and operator also. This involves plant control room and respective local areas staff. So total staff for a mega system, it could be of the order of 20, 25, 30, 35, not more than that, and they are monitoring the system from control room also and from the local area. Even if I put some instrumentation in the site, it is easier for a local staff to go and hear the noise and get a sense of it, why the temperature is going up, why the vibrations are seen today which are not there the case. So, that first hand information is communicated to the control room, and control room they will talk to the respective agency or people, whether it is a working hours or odd hours, that whole procedure starts for corrective action program. And here major activities are monitoring and plant control room and corrective action. The plant states may range from normal operation to deviation. Deviation could be transient also. That means in a very fraction of time, plant changes one state from another state, or it could be a slow deviation. Where we can track the deviation. But transients, it is like 0 or 1. Plant it was operating, it has come to the shutdown state. And alternate plant states, shutdown involving normal to postulated events. Any complex system, when they are built around the assumption that some event will occur. It cannot be avoided. They are called anticipated occurrence, and there is not much bigger threat. But if system goes from one state to another state, there are some inherent issues. So, they are called like power supply failure. It will happen once in a year or even once in 10 years, it will happen, but it will have its own frequency. But accident like situation like a breach in the system and all, they may they may come during the life of the plant, ranging from 40 to 60 years, or they may happen once in a lifetime. So they are called rare events. But monitoring is same for both the things through instrumentations. And then there is something additional component, walk down in the plant. There are certain 5% features which, if you don't visit the plant area, or if the site staff doesn't tell you, you will pick up that thing and some discussion will start and okay. So that what we see there, what is the deviation from normal operation, noise level, you can say, or some change patterns in the plant, or some new thing has been somewhere some spot was found, weight. That means somewhere some leakages were there, and that can be seen only in walk down actually. Otherwise, it will propagate into a catastrophic failure. So walk down to the plant, instrumentation room and area. There is very important testing and routine safety system. For routine safety system is very important. Because latent failures will show up sometimes in a transient way. So it is very important to look for latent causes which might be whispering something or which may not whisper something, but it will appear. The staff is trained to take periodic reading. So it is latent failure. It might manifest in terms of some process parameter reading change in those readings, and we have to understand that. So fault diagnostic techniques, real time and surveillance monitoring. This is a very important technique. Now fault tree technique. I had shown you some fault tree. Probably intuitively you will be able to see how the fault tree knowledge can be converted into diagnostics, because what we see there is a top event, that means an equipment or the plant. If I say fire injection system, then fire injection, how it can happen? So that is a cause effect analysis, okay, and we can develop the rules using this fault tree analysis, and we can develop an expert system, machine learning algorithm for fault diagnosis, not only for fault diagnosis but also for what action to be taken. So it is called precursor, or it is called antecedent and reaction. So those kind of things we have. And fault trees, there are some features. It's not only hardware component. Fault trees can take an input on human factor also, common cause failure also, and it's not that there is no provision for handling common cause failure. The plants are built considering various methods of isolation of common cause failure, treatment of common cause failure, and knowing a priori that these equipments can be a potential, can see a potential common cause failure because of environmental or ecosystems. Okay, sometimes distance factor, sometimes a separation factor, sometimes an elevation factor. If I have 3 redundant system and if I put them in one locality, so if the flooding situation comes, all the 3 will fail. So engineering and safety science has evolved to the extent that one will be located at other elevation. Okay, number one, that is at higher elevation, so that level rise will not affect all the 3. So second thing is temperature, humidity affects the electronics. Then there may be some symptom or signal which will show the degradation on line, or during if bit testing, built-in tests, some symptoms will be available. So common cause failure protections are there, but it can happen in spite of all those safeguard and provisions. So fault tree analysis is a very it embeds all the knowledge, and but again it depends on the level of detail we are going. See, it is up to an analyst to assume in a fault tree what is the basic component. Basic component, that means where fault tree ends, last leaf. A diesel generator can be last node for us, but diesel generators also, they have many supporting system like lube oils. I will be coming to those types, starting air system, lube oil system, fuel oil system, control systems, and breaker systems. So we will come to those details also. But fault tree, at this point you should understand that the detailing of the fault trees may require additional efforts to reach the subsystem supporting system, and in subsystem reporting system also individual component we should be able to go. So fault tree will give you an idea, yeah, this is the thing, but you have to go further. In fault tree we take wherever data is available and then we end there because data is not available. But when I talk about the fault diagnosis or prognosis, I have to go down further. That means we have to further go deeper, and that is how it can be called as a truly deeper learning, and deep learning algorithms are also there with us. So now let us see, I was talking about the fire fighting system because I chose this system because everyone knows fire, its consequences, and what is a fire fighting system. Okay. So this firefighting system comprised of A set, that is pump, motor and bearing, and B set, that is again two trains. Why we have provided two trains? Because we want redundant equipment. If this system fails, then this system should come. But again, we have one electrical power supply panel. So in most of the practical cases, even power supplies are separate. But suppose if they are having from the same bus, electrical bus, two different breaker, and that bus itself fails. So just for the simplicity, I have taken this electrical power supplies, both will fail. So then what will happen? This particular thing has become part of the common cause failure. That is electrical failure and leading to both the redundant devices. Otherwise, they are independent actually, pump, motor, bearing, maybe one separation in between. And then we have one valve. So valve A train, so valve A valve. So this is pump discharge valve, here also pump discharge valve. And what is happening is they are joining both of them to one header, and then it is a fire water injection starts. So, but then we have given only one valve. So common injection valve. So this has to go through the study of common cause failure category, okay, and then this water is sucked from this tank. So tank is also common, though a rare event. But if there is no water in the tank for some reason, whatever, so then this fire water tank also. But sometimes in the analysis you have to take some decision that structures, passive system, the failure probabilities are very low. So when I do a common cause failure, though in principle it is fitting into the common cause failure thing, but I can ignore that, because no leakage, and these tanks are required only when the injection occurs. Otherwise, we see level, and these levels are communicated to the control room. Any drop in this level 10% and will automatically I have not shown here, the tank will be brought to the normal level. This is the operation. So I can ignore this, but let us see how the fault tree will evolve. So this is our fault injection system, and they are located in what? I have shown here deliberately. They are located in a room, and it has got a small opening, because finally they are like any other industrial systems. Okay, so firefighting room is there. Deliberately I have shown because the room condition may affect a common cause phenomena in electrical power supply. It could be flooding also, it could be fire, even though it is firefighting system, this also has opportunity to see some fire event. So then it will affect the system adversely. So if we have understood this diagram, we go to the next slide and we see how fault tree looks like. So now we know that there are two trends I have given. So firefighting system failure, top event, okay, and independent event, I'm sorry, it should have been EI, So I, independent failure, and C stands for common cause failure. So we have, so in fault tree how it happens, this event will happen either this alone or this alone happens. So they have a path. If this event is reality, then the path goes up. If common cause event happened because of this down the line phenomena, it will, here independent failure is like two trains are there, independent train A and train B, you saw in the previous diagram. Both the train failure, end means both the train failure can only go to the top. In OR gate, any one happening input happening here, it goes to the top. It activates this node. It is called intermediate node. Okay. So and then finally from intermediate node, it can. But here I have given the redundancy in the system. The way in real time we had the redundancy, it has been shown over here. Now AND gate means train A and train B should fail to activate this node, and if this node is activated, then we have over here. So now common cause failures will be what? Water, no water in the tank. Okay, so I have considered here no water in the tank, injection valve failure, electricity failure, and human factor. Human factor means by mistake a common valve is left closed. It was not opened after testing. So it and injection failure occurs. A team worked on the electrical breaker, and they, while testing, you have to isolate the breaker. They did not remove the isolation. So human factor. Electricity, even if it is available, okay, and if it fails, then also it can lead to injection valves failure. That is a final valve failure can also lead to due to some component failure or due to human error or so because it is a single valve that should work. If I want to remove this probability, then I will put two valves in parallel, injection valve. So if both the valves open, if one valve open, our job will be done. But it depends on the design, and finally we have to do optimization, keeping in view the whole perspective. Here the gates are OR gate. This is the intermediate event, OR gate, then AND gate. Okay, so I should write OR gate here. Transfer gate. That means you can transfer this input and you develop it on some other page. So independent TA and TB has been developed on the next page actually. So what happens? Independent TA, pump A failure, motor failure, valve failure, and bearing failure. And pump failure means what? It could be pump A failure. It is leakage. It is a mechanical seal failure. Mechanical seal is something which doesn't allow water leakages from the pump. Pump shaft is rotating and the socket is having a stationary. Now leakage will occur, but mechanical seal type of components are there which avoid leakage of water from there. Like you might have seen generally when pumps are provided with gaskets and all that, some leakage occur. But when for certain things, mechanical seal is so the rotating shaft will be rubbing across the stationary shaft and provide the sealing. This sign indicates undeveloped events because motor can have its own failure, but I have not developed it. And then this same fault tree is applicable for B also, and we got the independent DB. So if this pump fails, since it is OR gate, here also OR gate, and top also fault tree, it is OR gate, it will pump A failure itself will activate the thing. But again we have AND gate there. So even if this TA fails completely, it will not reach top. Both the things have to fail. Both the TA and TB has to fail. TA and TB has to fail to give the final output. So TA alone, though I have written TC, it is a TI. So so here TI will be activated only when TA and TB both the fails. Okay, and if that happens, then output goes to the, so that means fire system failure. If one fails, then output will not go on top. That condition is end condition. But here, one of the event happens, it goes to the top. So this is how it can be converted into knowledge. So looking at this, how I will develop the rule. So I will develop the first rule, fire failure, fire system failure, independent C failure or independent CCF failure. Okay, and how independent C failure, this part C failure occur? This will occur as rule independent A and independent B gets activated. So the second rule has come into picture. CCF C failure is water or injection or electricity or human failure. So like that we write production rules and develop an expert system. This is simple logic that I am inventing. When you do at the plant level, thousands of the rules are there, and there is an inference mechanism, there is a data, because sometimes this may not be qualitative input. A signal, a process parameter has to touch certain value, and that is some real number. Okay, if that is then failure. So for all the component what we have here, we have put here, there is a failure definition, and that definition becomes very important when we develop the rules, because those rules are activated when anything goes wrong or any deviation occurs. So we have seen the fault tree and how we can develop the production rules for diagnostics. Now event tree we have brought, whatever injection failures are there, finally they will become part of this, and then we will know safe, unsafe. So our criteria or our severity will be dictated. If it is safe, be happy, nothing to be done, it can remain down, but whatever plant requires, you have time. But if it is unsafe category, you have to take immediate action. So that risk or severity things are brought in to diagnostics through event tree methodology. Okay. And here you get the probability also, there is a quantification also. So these rules can take high priority when we land up into this kind of situation, injection failure, and here also it is an injection failure, here also it is and they are all unsafe. This is fishbone diagram. You have a cause and effect, So cause could be some fundamental metrics have been given. It could be contributed by measurement, it could be by men. Actually we should say human, because men and women both are contributing to the this present ecosystems equally. Environment makes the whole difference. If they are not specific, and it will be different. So what can be the things, we will see through one case study. And then machine has its own contribution methods, and then we have to connect the dot over here, how it becomes a reality. One machine, something went wrong, it was man was there, and it was a environmental and material related concept that led to the undesired. But we will in a diagram will have all the three probabilities over there actually. So let's see now how practically a fishbone diagram looks like, So causes, the causes we have here on this line. Measurement, calibration induces some problem if it is not correct. Parameters or measurement create some problem. I am just giving some example, how the dots can be connected. And then when we talk about the machine, lubrication, bearing, electric breaker, these can contribute to the, these are the causes that are there which can happen. Man training, human error, institutional failure. In fact, this can come here or this can come here also. So then environment is now plant, policy, quality and humanity. Many times quality related issues, they can become part of the injection failure. So this applicable fishbone diagram we have drawn for injection failure. Erosion, aging, corrosion, these are routine things. So some it can this, and then methods, testing, maintenance, surveillance, that can lead to. So you can say it can travel from this end, what are the problems, and finally how it can define the injection failure here. Okay. So it has got all the attribute. Fishbone diagram could be complicated also. There could be one or two more you can say header elements can be there depending on the domain that we are operating. If it is in defense, fishbone diagram will be different. If it is in nuclear defense, fishbone diagram will be how radiation can affect my electronic system performance, that also can be seen actually. Chemical industry, they can have their own causes and failures and all. So it depends. So domain specific aspects have to be, this is just generic injection firefighting system is a very generic example, and it is better to understand from generic example. Now Pareto analysis, the 80-20 rule is the thing. That means 80% of domain specific issues can be traced to 20% causes. If we can find out or correct 20% causes, 80% of the problems, it is a very powerful statement. Okay, and Pareto analysis has this at the center actually. It also provides a ranking. So if I say 80% or 20%, so I should be able to rank them actually, you know. So 80% failure and 20%. So I should know, what is important is I should know 20% causes to address 20%. So define the problem, core Pareto philosophy, 80-20 rule, analysis, simulation, and binning up the causes of any identified component. Okay, and diagnostics for failure. So this completes here, and that's how Pareto analysis is performed. Okay. So output of the so let's say we are talking about injection failure. Everywhere I am taking injection failure as the, so power supply was the cause. You can see that power supply was common. Probably this analysis, if we do, we will have separate power supply for both, because there it is ranking very high. 7 events are there of power supply failure, and bearing failure, this is second, 5 failures are there. So that means and then they contribute to, this is 100% failure, and they once they touch, so easily they touch here. So this has to be reduced, and this is very important information we get. And quality and surveillance, their events are less, and we can improvise, we can be, but then here in this case we have to do a level 3 root cause analysis, but here we can do a simply level 1 root cause analysis to, and what is level 1, level 2, level 3, that we will discuss. At present you understand it requires very high attention, and the root cause analysis is a resource consuming option. So but we have to apply here because the number of failures and they contribute. So let us say how we are meeting the 80-20 rule. First 2 causes total, 12 out of total 15 causes, 12 causes, these 2 causes, 7 plus 5, it makes 12 out of 15 causes, and that means they address 80% of failure and need immediate action. The 2 quality and surveillance can be fixed. So this will happen only when this Pareto chart will happen when I have data with me and I plot them, I rank them, I see how they are comparing and contributing to 80% of the failures actually, you know. So this is Pareto analysis, and what we have discussed, Pareto and other root cause analysis techniques, and now 4th lecture is on root cause analysis.